There is an object moving through the upper atmosphere right now. That technically, according to the physics textbooks written 20 years ago, should not exist. It is not a satellite, and it is definitely not a conventional aircraft. It is moving at more than 5 times the speed of sound, wrapped in a sheath of superheated plasma so intense that it turns the surrounding air into a glowing, destructive blowtorch. At these temperatures, metals don't just weaken. They melt like ice on a summer pavement. And yet, deep inside that fiery inferno, microprocessors are cool, calculated, and actively changing direction for decades. Intelligence agencies in the West were convinced that guided flight under these conditions was impossible. They assumed the intense heat would blind any sensor, fry any computer, and tear apart any control flap that tried to steer. But then, an unannounced orbital test shattered those assumptions in a single morning. A flight path so unpredictable, so fast, and so fundamentally different from traditional rocketry that it left defense analysts staring at their tracking screens in absolute silence. The real danger wasn't just that the weapon worked, but that it bypassed every single early warning radar system ever built. Without firing a single weapon at them, to understand how an engineering impossibility became a global reality, we have to go back to a quiet room in Virginia where the math simply stopped adding up. It was during a routine review of satellite thermal imaging, when tracking operators noticed a strange anomaly over a desert testing range. A thermal plume appeared, expanded instantly, and then completely vanished from high-orbit sensors. Normally, a long-range ballistic missile follows a predictable path, like a thrown baseball. It shoots high into space, follows a clear arc, and comes down on its target. That arc makes it easy to track, easy to calculate, and theoretically, easy to intercept. But this object didn't follow the arc. It shot up, flattened out just inside the upper edges of the atmosphere, and began to glide, skipping off dense air layers like a flat stone across a calm pond. By the time ground-based radars tried to lock onto its location, the object had shifted its trajectory by hundreds of miles. It was maneuvering at speeds where traditional defense systems cannot process calculations fast enough to predict the next turn. And that's when a chilling realization hit the analysts in that room. The multi-billion-dollar defense shields built over the last 40 years, designed to look high into the sky for incoming arcing missiles, were looking in entirely the wrong direction. But nobody could understand how the hardware survived the journey until researchers began looking into an obscure series of academic papers published years earlier. Decades ago, a small team of materials scientists began working on a problem that most aerospace firms had abandoned as a dead end. They weren't looking at bigger engines or more powerful explosives. They were obsessed with ceramics, specifically synthetic compounds designed to endure temperatures hotter than the surface of some stars, while the rest of the world was focused on stealth coatings and radar-absorbing paint. This group was forging ultra-high temperature tiles that could withstand structural forces capable of snapping solid steel like a toothpick. They tested these materials in deep, underground wind tunnels, built specifically to simulate the brutal friction of extreme atmospheric flight. For years, project reports were filed quietly, hidden inside routine civil engineering budgets, attracting zero attention from international observers. Western intelligence viewed these facilities as outdated research hubs, unaware that they were laying the groundwork for a revolutionary leap in manufacturing. But building a heat shield was only half the problem. The real nightmare was learning how to steer through fire. When an object travels at these extreme speeds, the air molecules in front of it compress so violently that they strip electrons from atoms, creating an envelope of ionized plasma around the vehicle. This plasma acts as a total radio shield. No signals can get in, and no signals can get out. For decades, this was known as the reentry blackout, an unavoidable period where pilots and automated systems fly completely blind. If you can't receive targeting updates, and your internal sensors are blinded by superheated gas, a maneuvering missile becomes nothing more than an expensive, unguided piece of falling space junk. Engineers knew that if they couldn't solve the blackout problem, the entire weapon concept was useless. So, they stopped trying to punch signals through the plasma envelope and started using the plasma itself by developing precise electromagnetic field generators inside the nose cone. They found a way to manipulate the ionized gas around the vehicle, shaping the plasma to act as an antenna and a steering mechanism at the same time. The very barrier that kept Western systems blind became the guidance tool for the new weapon, and that's exactly where everything changed. In the late summer of 2021, a test launch took place that caught global defense communities completely unprepared. A rocket lifted off, carrying a payload into near-orbital space, but instead of dropping back down toward a target, the payload detached, flew around the globe, re-entered the atmosphere over an entirely different vector, and glided down to its test grid. It wasn't just a high-speed vehicle. It was a global-range, highly maneuverable, untrackable glider. Military planners had built entire defensive doctrines around the idea of distance. They relied on aircraft carriers, floating airfields protected by an impenetrable wall of radar, destroyers, and interceptor missiles. The logic was simple: keep the enemy at a distance where they cannot reach you, and you control the ocean. But a weapon that glides through the atmosphere at extreme speeds, continuously changing course, completely flips that mathematical equation on its head. A multi-billion-dollar warship, designed to project power across thousands of miles, suddenly faces a threat that leaves commanders with less than 45 seconds to make a decision once detected. The math behind this shift is brutally asymmetrical. Building a modern naval fleet takes decades, hundreds of thousands of personnel, and hundreds of billions of dollars. Building a hypersonic glide network costs a fraction of that investment. If a strike group has to operate hundreds of miles further out just to stay beyond the reach of these gliders, its tactical effectiveness is instantly neutralized without firing a single shot. The threat isn't just about destroying a target, it's about denying access to entire oceans. When word of the successful orbital test leaked to the press, government officials tried to minimize the news, calling it routine research, but behind closed doors, emergency committee meetings were convened, and long-term procurement budgets were rewritten overnight. Defense contractors were summoned to present emergency solutions, but the engineers delivered a sobering message. You cannot simply update the software on existing defense missiles to catch something moving this fast and maneuvering this unpredictable. To shoot down a target like this, you need interceptors that can move just as fast, withstand the same extreme heat, and maneuver with the same impossible flexibility, and that means starting from scratch. Modern defense development cycles usually take 15 to 20 years from the drawing board to actual deployment, but the timeline set by this new reality doesn't give anyone 15 years. While Western defense firms scramble to design high-power lasers and space-based tracking constellations, the new missile systems are already being produced, deployed, and integrated into operational units. The immediate focus has now shifted to space. If ground radars are too low, and traditional satellites are looking in the wrong place, the only option left is to build massive constellations of thousands of low Earth orbit satellites. These sensors must track the faint heat signatures of these gliders as they skip across the atmosphere, relaying targeting data in milliseconds to defensive platforms. But building such a system requires unprecedented technological coordination, massive industrial capacity, and continuous rocket launches for years to come. Yet, even if this satellite shield is successfully built, an even deeper problem remains on the horizon. The technology isn't standing still. The first generation of hypersonic gliders relied on pre-programmed strike vectors. The next generation, currently in active development, is incorporating real-time artificial intelligence to coordinate multiple gliders simultaneously. Imagine a swarm of these weapons, talking to each other at Mach 10, sharing targeting data, and executing synchronized, multi-directional strikes on a target defensive grid. When weapons move faster than human reaction times, decision-making must be handed over to automated computer algorithms. And when computer algorithms are tasked with making life-or-death defense decisions in fractions of a second, the margin for error vanishes entirely. A single false sensor reading, a glitched satellite feed, or a miscalculated trajectory could trigger an automated defense response before human commanders even realize a launch took place. The sky above us appears calm, silent, and unchanged, but far above the clouds. In the thin layers of air where friction turns wind into liquid fire, the rules of international security have been fundamentally rewritten. The Pentagon isn't just paying attention to a new missile. They are staring into a future where the traditional tools of power projection no longer guarantee safety. The race to build a working shield is now moving at breakneck speed. But as scientists push the absolute limits of physics and engineering, one terrifying question remains hanging over the global strategic balance. What happens when the weapon reaches its target? Before anyone even realizes the war has started.